Hello, my name is Joshua Chanez. I'm an electrical engineering student at the University of Texas at El Paso, and this summer I focused on design techniques for optimizing 3D printed antennas. Now, it's no secret that 3D printed antennas is sort of a dying art in the industry for the Army. It's just slower to produce, it's more expensive, and it doesn't perform as well as your conventional manufactured antennas. So this is due for two reasons. Fabrication takes too long and the performance is not quite there. There are a lot of researchers that are already working on the fabrication of these printed antennas, so I decided to focus more on its performance. So throughout this research, I explored different methods of improving this performance in a printed antenna that's applied over a complex surface. The first issue we ran into was applying antennas over a curved surface and how its frequency response shifted. Every antenna has an important characteristic called its frequency resonance, and this is the frequency at which your antenna is able to receive information from. If this frequency is off by a little bit, it may not be able to receive the information it wants to. So this is directly related to the size and the shape of the antenna. When you're applying these antennas over a curved surface, specifically through means of projection, the sides of the antenna tend to stretch out a little bit. That change in dimension and size leads to a shift in that frequency. Over here we have an example where that frequency is shifted 0.25 gigahertz to the left. To combat this, rather than projecting the antenna over the surface, we decided to add a wrapping technique that shrinks the antenna before placing it on the curved surface, maintains the dimensions of the antenna, and makes up for the frequency shift. It also gives us a smaller antenna to work with, which means we could fit it into tighter areas. On the topic of smaller antennas, there is another technique called profile miniaturization, where you could see it more clearly in a dipole antenna. You can add some sort of serpentine design to crumble up this dipole antenna, making it smaller and keeping that same frequency response. This profile miniaturization makes the antenna smaller, allows you to fit it into tighter areas, and it comes with a gain boost. We don't quite understand why yet, but this is for future research purposes. If you would like to improve on your overall gain and directionality, you can also add a reflector to the quarter wavelength of your antenna. This is basically a conductive pad that redirects all the energy that produced to one end back out the other way. Over here we could see that it not only funnels the signal to one direction, but it also triples its throughput. Finally, to make sure all of this connects seamlessly, we wanted to explore different connection integration methods, mostly easy ways we could connect SMA connectors to your antennas, basically ensuring that there is no reflection from the connector to the antenna. This is called match impedance. And this topic actually led me down a rabbit hole of new discovery. I realized that there's fundamentals that I have yet to explore in sciences behind the coupling that occurs in a straight line strip. In this discovery, I was also able to use that inductance feature that most of the loss comes from to actually connect two cables together without having them touch. You see, when energy runs through a trace, it emits electromagnetic waves from the side. That's where you lose most of your signal. Now, we wanted to use this feature to bridge a connection between one trace and another, to have them both connected without having them connected. This was introduced in a folding antenna project that I was approached with. To conclude, you'll have best results out of your project if you sort of combine all of these features together, it provides you with that flexibility of printing in complex surfaces. You don't lose any of that performance that we wanted to, that we were so worried about keeping. And essentially, we're not trying to replace the conventional market for antennas. We just know that there are certain projects that they require more space, they require less weight, and they're willing to spend a little more time fabricating and spend a little more money fabricating more custom antenna structures for just for the sake of being able to carry more weight, insert more hardware, maybe load up more payload. The applications are vast, but still niche enough to where it won't be causing any disturbance in the manufacturing world.